So on to the third part of the Weller saga. I figured out that from the past two videos on this, I realized the solder joints on the board and the ground connections were bad. I think if you looked at the other videos, you'll see there's kind of out of focus here. Just a moment. Go back to autofocus. So yeah, there's issues with solder joints and things like that, which I'm going to get to in a bit. I'll fix that after, but I wanted to check that the pencil portion of the iron is intact too, because these are known to have issues, and a lot of people have done videos on them and so forth. And I've certainly been through a couple of them on this base station. I'm not running on the original pencil that it came with. Let's give ourselves a little more light here. Yeah, this has failed. I'm trying to think if this is the second one or the third one I've had on this particular station, but yeah, the first one I had, the cabling failed, right roughly in here near the end of the handle, which is a very common problem. The wires get kind of twisted and mangled up in there, and often they'll perforate their sheathing and short out to one another. Things can get very interesting. On this one in particular, everything is fine except the ground is open circuit, so there's no continuity between pin 5 on the connector, which is supposed to be a ground bonding pin that goes to the mains ground, and that should go to the casing of all the metal parts of this. The way this is designed, actually, I'll go on a little tangent here. There is something smart they did. The iron there's 5 pins in here. 2 for the heater, 2 for the thermocouple, which senses the temperature, and the 5th, as the last one, is for the ground. The thermocouple, 1 pin of the thermocouple in here, right in the end, is tied to chassis ground. And the idea behind this is that if you tie the circuit signal ground, essentially the analog signal ground, to power ground somewhere, the best place to do it is in one place only, so you don't have ground loops, but also as close to the sensor as possible, so that you're not going to induce error voltage across anything that'll offset the sensor signal if you happen to touch something while you're soldering that has any kind of a path back to power ground. And that is a common thing that will happen, especially if you're trying to do ESD safe work, static discharge sensitive work. You more than likely have something grounded, and there's a lot of misunderstanding about this. I could do another video on that. There's some really good videos on the net already, but essentially you actually don't want a hard ground to anything anyway. For ESD sensitivity, you want a dissipative ground. The reason for that is if ESD is all about potential difference, it actually doesn't matter what potential everything is referenced to as long as it's the same potential. But again, ESD occurs because there's potential difference. There's charges stored on your body, on objects, so on and so forth, that differ from the potential on some other thing. And it's when they come together through a conductive path that a discharge occurs, which can pass a significant quantity of current and destroy the oxide gates in transistors. Is usually the thing that goes bad. It can wreck other stuff too. So when we say dissipative ground, we just mean resistance. You want to have enough path conductance to get rid of the current necessary to prevent charges from accumulating, but also to transfer charges between things of different potentials, at least somewhat gradually. So you deal with things quickly enough that the charges don't produce, don't stick around, but slowly enough that you don't get these giant current pulses. Anyway, I'm going off already on the ESD video tangent, which I just said I wasn't going to do. The point is, these are grounded in here, which is actually the right place to do it. And you'll find that when you take one of these apart, there's no other ground between the electronics on the secondary side of the transformer and mains ground. And that's intentional. And you'll notice if you look at the board, actually, you'll see there's a fuse. This little guy here is a 200 milliamp surface mount fuse. Might even be a poly fuse, I'm not actually sure. But it goes between the signal ground and the thermocouple circuit, and it's presumably there so that if you short this thing out on some object you're working on, you don't blow up all the circuitry. So that's there as well, and that's kind of important. But yeah, if you're getting erratic operation, and they mention this in the manual actually for these, I don't know if it's in the service manual or in the user's manual, but it's definitely in the service manual. If the power ground, like if you cut the ground prong off the cord, or you're connected to an ungrounded electrical circuit, a receptacle, the temperature control can end up being erratic. But for the same reasons, if the ground is lost in the cabling or in the pencil, the same thing can happen. And I have been experiencing these strange issues. I think it's a combination of more than one, because you saw on the board there's these broken solder joints. That's a problem. But again, I've found that the continuity between pin 5, which is meant for ground bonding, and the stainless steel casing here, there isn't any continuity. It's open circuit. However, I do see continuity from here to the thermocouple, which is good. That means that's still bonded, which makes sense. If you look in the end of this thing, you can kind of see it. In that little central tube that's coaxial with the pencil is the thermocouple, and the tip actually, when you install it, has a bore cut into it. It slides over the thermocouple. And the concept behind this is that the thermocouple has a fast response. It's going to get some idea of changes in tip temperature fairly rapidly. But anyway, the thermocouple is actually welded to the inside of this bore, partly so it stays put, partly so it gets good thermal conductivity, but also just, there you go, you've got solid ground bonding in the best possible place where there's very little resistance between the signal ground and the power ground along some path across which you could drop voltage, which is then amplified by the thermocouple amplifier and measured as temperature error. We really want to avoid that, and this design does that very effectively. So now the interesting part of the video, and really the reason I wanted to do the video in the first place, was actually about how you get this pencil apart, because I've seen a lot of different people do different ways, and everybody seems to be finding their way in. It's a little bit of a pain, but I haven't yet seen anybody take advantage of the fact that there's a threaded shaft here that you could use to turn this thing into its own puller. I see people doing all sorts of other stuff. They're grabbing onto this with needle nose pliers and crushing the heater tubes. And by the way, if you see the little swage along here, that was me. I actually did that deliberately to I think what it was the there's a ridge in here, kind of can't really see it, a step in the shape of the inside of the tube. The tip has a shank on it, or whatever, that sits in that, and it stops on that, so it prevents it from sliding in. And when you tighten the tube down onto it, here's the tube, it's pulling the tip in there. And what I found with these, again, is another bit of a, I don't know, cheapness or design flaw. They loosen up because they're hot and cold and hot and cold all day long. And the tip slides its way in, and it actually gets stuck in there. And it can get so stuck you cannot get it out without wrecking the iron. So I swaged this a little bit to increase the shoulder in there so that the tip can really sit down on something. And that way this holds it relatively tightly, but doesn't let go. I would honestly change the design of this. If I designed it, there would be some springiness in somewhere included so that it would maintain constant force on the tip, regardless of the change in length, the contraction due to the expansion and contraction due to the changes in temperature. this is a rigid design, and rigid designs are a bad idea when you have wildly changing temperatures. It's the same reason well-designed automotive engines use long head bolts. The longer they are, the less the amount of clamping force changes with dimensional changes. It's a very, very important concept in mechanical engineering. So yeah, this could be improved dramatically by, for example, if we were to take this nut off of the tube and modify the design of the tube so that there's a, just a stiff, relatively short spring hanging out in between the flange of the tube and the flange of the nut, so that when they're pulled together, instead of just tightening right down, it just compresses the spring just enough that there's a little room to compress a little more or to expand without losing, without changing the force very much. That would mean that you can tighten this thing down as hard as you want. The nut stops on the abutment. The spring is compressed but not fully. The tip would no longer try to force its way into the barrel. If you over tighten it, you couldn't over tighten it, and it would adjust automatically to changes in dimensions due to temperature. So this is just me thinking out loud about ways of improving things. I'll probably never do that. It's just how I would design it. But anyway, yeah, pulling this apart, all you need to do is have something that's going to push back on the plastic and forward on the metal. It's very simple. So you find yourself a nut that'll thread onto this. I didn't check the size, but I'm pretty certain this is an inch size, and it's a fine thread, and it looks like it's probably 3/8 NF. Probably. Don't take my word on that. It does fit a 9/16 wrench properly, so I doubt it's a metric. And it's a Weller, it's American, so it's probably not metric. And just find yourself something that's going to be wide enough, opening to fit past the steel parts and touch only the plastic. And there's kind of a nice little surface there. It's curved, which is unfortunate, but something that's maybe not too sharp. This has a bit of a smoothed edge on it, and just put that over there. Maybe put down a washer so the nut doesn't have to slide on it, and you run the nut on here, and you should be able to tighten this up. And up until the thing bottoms out on the shank on the steel, it will push the plastic off the spline on the steel backing in there. Most people agree that it's best to heat these up before you try to pull them apart, and I think that's a sensible thing to do. So I've never tried this before, by the way. I have taken these apart all sorts of other ways, and I don't know why it didn't occur to me to just use a nut threaded on, but I'm going to make a little bit of noise and use the heat gun here, and I'm going to warm this up till it's, not like really hot, but fairly hot. And then I'm going to try this method for the first time. We'll just see how it goes. I enjoy showing people, letting them have a front row seat on my ideas sometimes, and to discover something for the first time along with me. It might fail catastrophically. I have a feeling it'll work really well. So let's give this a go. Time for some noise. And actually, it's prudent to avoid heating the plastic. And maybe I'll just sit this over here, just to deflect some of the heat away from the plastic. Should be okay. I mean, there's all sorts of ways of doing this. I'm just kind of winging it. Do the old boiled water test. That's pretty good. So Try not to waste too much time here and have this thing pull off on me. And wrench. Let's see if that works. It feels right. And one thing you got to watch out for, and I should have mentioned this before, you want to be really sure the cord restraint is letting go. Otherwise, this thing could pull the wiring out of the heating element end of it, and if you do that, you're screwed. So you want to see as you turn the wrench if the, oh, and I just bottomed out, so that's good. You want to see the wire kind of moving. If it's not moving, maybe stop and just make sure it's not stuck. So there you go. You can see some of the splines sticking out. So that is definitely successful right off the bat. So all I need to do is increase the height of this thing a little bit, and I can do that with some washers. Would have made sense of me to find more washers before I start the video. Here's something sitting here that looks, it'll fit. It's maybe too thick. Pull that off. Just perfect. Okay, we can get the nut to start threading on there again and go for a little more. Just right. Okay. Look at that. It's eased off so much I can just do it by hand now. Oh yeah, look at that. Very nice. I could finish it off with the hardware, or I can do it by hand, whichever. Yeah, it's eased right off. Now I'm noticing I can tell just by my feel that there's not just the friction of the plastic on the metal. There is some tension in the wiring. I can feel that. You want to really be trying to notice if that's there. So I'm pushing on, because I kind of know what's in here. There's a metal clip crimped onto the outside of the cable sheathing. That's actually part of the problem with these. They get their tensile strength for the cord restraint via the outside of the cord, which is totally the wrong way to secure a cord. Well-designed cabling, it's usually a little more expensive, has a tensile strip inside, a stringer of some sort, and it's usually going to be jute or some kind of rope or string. It can be nylon, it can even be steel cable. But that is the thing you want to anchor to because it's not stretchy. The rest of the stuff in there is a little stretchy. Even the copper wiring is a bit stretchy, and you just don't want all of that stuff getting yanked on. So you just shove this in a little. You can feel it hit the little crimp thing, and try to pull it out. Anchor yourself to brace the wire, so you're pulling on that instead of the barrel, and just have to slowly work this thing out by, don't ever pull on this, you'll destroy it. Try to, if you can, push it out. So, well, that's going in a fair bit, so there's something else going on here that's holding it up. A little bit of junk. It's not coming out. I don't want to pull on that. So I might be forgetting something. There might be a bit more stuff in there that holds on to things. I don't know. So I'll fart around with that. I won't waste your time on the video kind of shooting in the dark. But that's how you, well, I sound like a dick if I say, oh, that's how you do it. There's probably a lot of ways of doing this. This is one way that I've discovered that I just hadn't tried before, that I wanted to suggest to everybody else because I thought it was a good idea, and it sure is. It worked very nicely, and it was no stress. And it's a very controlled way of pulling. You're not, pulling with your hands where you're going to you know what it's like. Humans are constant force, not constant displacement. Nobody has very good control of position, but they have pretty good control over how much force they're applying. And that's the problem, is if something lets go, you can't stop applying force as fast as you need to. You're going to overshoot and pull too far. So it's much better to have something that is going to self-limit, and you can feel what's going on, and you're not going to yank it 5 inches out. It'll just stop in a few thou. Anyway, that's that. I'll probably maybe have one more video on this once I get it opened up and see what's wrong, but I'm not gonna kind of meander through this anymore because I'll just use up time. So there, have fun.